Number 15 of transport phenomena in mesoscopic and nanoscopic systems. And in the last day we were discussing the case of M contact atoms, which are basically coupled to these N atoms in the channel, and then we considered this channel as an entire unit, and we considered this contact as an entire unit, and we wrote the discrete form of Schrodinger's equation, which is the matrix version of Schrodinger's equation in this format. Okay, here I repeat that this Hamiltonian H, this is the Hamiltonian of the isolated isolated channel. Okay, so let me write it here. H is Hamiltonian for isolated channel. Okay, isolated means this channel is not coupled to the contact. HR is the Hamiltonian of isolated contact. And this tau and tau dagger are basically the coupling matrices which couple the channel with the contact and the contact with the channel respectively. Okay, so and we argued that this equation we can basically get rid of this matrix HR, or we can incorporate the effect of this matrix HR by writing an equation in the form of E psi equals to H plus sigma psi plus S. Okay, now I repeat again that why do we want to incorporate the effect of this matrix HR or this contact Hamiltonian HR via this term sigma and S? This is mainly because HR is typically large and the contact is typically semi-infinite. That's why we typically try to reduce the entire computational burden by incorporating this matrix H, the effect of this matrix HR into this matrices sigma and S. So let's just see how to do it. Let's first consider the case, the simplest case actually, where there are n atoms in the contact and these n atoms are coupled to the channel, which is this atom. So the channel is the 0th atom here, the level is marked as 0 here, and this channel atom is basically coupled to the contact. So this portion, so to the left of this line is basically the contact, and to the right of this line is basically the channel. Okay, and this channel is basically coupled to the contact, and the channel consists of one atom over here. This is the kind of the simplest case. So let us see how this sigma and S would look like in this case. So note that if this atom, if this channel atom was not coupled to the contact, in this case what would be the equation, what would be Schrodinger's equation written in discrete format or in matrix format? So it would be just E psi equals to EC plus 2T0 psi. Now if it would be coupled to atoms towards the left and towards the right, then we would have these two terms also, minus T0 psi minus 1. So this is the minus 1th atom, and then if there would have been one atom over here, then this would be minus T0 psi 1, where this is the one atom. Okay, but since this is not coupled to the contact, we are considering the isolated case right now. We would only have this term because this atom here we are assuming is not coupled to either this psi minus 1 over here or psi 1 over here. Okay, so this is the case of isolated atom. So case of isolated channel. Okay. Now once we couple it to the contact, what would this equation look like? So now if it's coupled to the nearest atom, that is, we assume that the coupling between these two atoms is negligible, so an electron cannot directly move from here to here or here to here. Okay, in that case, assuming that the channel atom is basically coupled to its nearest atom, that is this atom over here, in that case we would have minus T0 psi of minus 1 over here. So this is the minus 1th atom and the wave function here is psi of minus 1. Okay, similarly here it's psi of minus 2, psi of minus 3, etc. Okay, I will just call it psi 0 over here to denote the 0th atom is the channel. Let us instead to differentiate it, let us actually call it by the letter phi, just to differentiate it from the channel. So phi are the corresponding wave functions of the contact and psi is the wave function of the channel. So let us write in that way, because that way it's easier to differentiate. Now for the isolated channel, if this channel would have been isolated from the contact, okay, then in that case for isolated contact, what would the equation of all these wave functions in positions look like? So the equations for an isolated contact basically satisfies an infinite set of equation, which kind of looks like this. E phi n is equal to minus T0 phi n minus 1 plus EC plus 2T0 phi n minus T0 phi n plus 1, where n is less than 0. Now once we basically couple it to the channel, once we couple this contact to the channel, in that case the contact consists of many atoms, so it's a semi-infinite structure and the channel only consists of one atom. So the contact can influence the channel, but the channel cannot influence the contact because the channel is small, the contact is large in dimension. Okay, so in that case this equation over here is not violated, this equation still holds because the channel is small. So coupling the contact to the channel does not influence the contact. Okay, and in this case if the channel is coupled to the contact, we can actually remove this isolated contact from here and we can simply say that the contact properties are not changed and phi 0 is equal to psi. Okay, so we just rename this this wave function in the 0th atom as phi 0. So it's just a change of notation and nothing else. So it does not change anything, it's just a change of notation. And because, as I said, coupling the channel with the contact does not change anything about the contact, so the EK relation of the contact still holds. Okay, if you dope silicon with 1% phosphorus, then the dispersion relation or the EK relation of silicon does not break down, it still holds. So like that, on coupling the channel to the contact, the EK relation of the contacts or this equation for the contact still holds. Okay, so I have done nothing here, I have just renamed this psi as phi 0, just a change of notation, so that for n equal to 0, so that for n equal to minus 1, this thing here becomes equal to phi 0, which is basically psi. Okay. Okay. Now we already know from our previous discussion that this kind of equation is basically satisfied by a wave function of the form phi n equals to b e to the power I k n a, okay, where n denotes the atomic number or the lattice point number, and then this is a forward propagating wave. So we can also add a backward propagating wave to the solution, because this also forms a solution of the Schrodinger's equation, of the discretized version of the Schrodinger's equation. So C e to the power minus I k n a. So this part is if this time dependence is denoted by e to the power minus e by h bar t, then this part basically forms the forward propagating wave. So this is the wave that propagates from the contact into the channel, and then some part of the wave should also be reflected back into the contact, because the contact contains many electrons, so not all electrons can enter inside the channel, because the channel has smaller capacity compared to the contact. So this is a backward propagating wave, kind of which is reflected from the channel. Okay, so this is kind of the backward propagating wave. So this is mainly reflected from the channel. Now we have also seen that if this is the solution of this equation over here, the discretized version of Schrodinger's equation, in this case the energy E, if we put this solution over here, and if we put the solutions of phi n minus 1 and phi n plus 1 over here, then this energy E basically becomes E equals to EC plus 2T0 1 minus cos Ka. So this we have already seen before. Anyway, this point is not required here. I just stated it to remind you. This is not required, so I will just remove this part from here. Now from here, if we note that this phi 0 is equal to psi, so if we put this 0 over here, if we put this n equal to 0, in that case this basically becomes psi equals to phi 0 equals to b plus c. Now what is the equation for psi? So the equation for psi is basically E psi, which is again phi 0, is equal to EC plus 2T0 psi plus minus T phi of minus 1. Now we are interested in only this equation, because this equation basically determines what is happening in the channel. We are not interested about what is happening in the contacts, because the contact is large and the contact does not come into picture, it's semi-infinite, and we know that it has quasi-equilibrium statistics. So we are interested in the channel, because it is the channel which governs the properties of the device mainly. Of course the contact also influences, and the contact to channel coupling, okay, how well the channel is coupled to the contact, that also influences the properties of the device. So how well the channel is coupled to the contact, that is determined by this parameter T0 over here. So anyway, we are interested mainly in this equation, but okay, let me reframe the statement. We are mainly interested in psi actually, okay, because this is the wave function inside the channel, but this psi basically depends on phi minus 1. But we are not interested in phi minus 1, phi minus 2, phi minus 3, etc., because they are wave functions in the contact, and we already know that it is in quasi-equilibrium statistics, and we do not have anything to do with the wave function in the contact. If we know the wave function in the channel, we can determine the properties of the channel, or how much current is flowing through the channel, etc. So our intention is basically to remove this phi minus 1 from here by appropriate parameters. So what we do, we just write the equation for phi minus 1. So our intention is to get an equation with psi as the unknown parameter so we will replace we will have to make appropriate replacements to incorporate the effect of phi minus 1. Okay, so what do? We just write the equation for phi minus 1 here. So phi n is equal to b e to the power I k n a plus c e to the power minus I k n a. Okay, so phi minus 1 is just b e to the power minus I k a plus c e to the power I k a. Okay, now from here we note that this is the forward propagating wave and this one is the forward propagating wave, and this is the backward propagating wave, and then we have information about the statistics of the forward propagating wave. Okay, because for the forward propagating wave the occupancy probability is determined by the Fermi function. Okay, for the forward propagating wave, how much is the probability of the wave to strike the channel, that is basically determined by the Fermi function, but we do not really have information on the backward propagating wave over here. So we will try to make appropriate replacement for this one. So we see that this wave function psi is equal to b plus c over here. So what we do is we replace this c by the psi minus b from this equation over here. Okay, so p to the power minus I k n a plus psi minus b, sorry, this n is not there, so e to the power minus I k a, e to the power I k a. So this basically becomes b e to the power minus I k a plus e to the power I k a, sorry, we have this minus sign over here, plus psi e to the power I k a. So this is twice of sine term multiplied by I. So this is equal to 2I b sine k plus psi e to the power I k a. Okay, and this is what? This is phi of minus 1. Okay, so from this equation over here, let me go back to the previous page. So if we make the replacement of phi minus 1 in this equation, what will we get? So the entire equation was E psi equal to EC plus 2T0 psi minus T0 phi minus 1, and we make this replacement for phi minus 1 from here, put it here, and then this becomes EC plus 2T0 psi minus T0 psi e to the power I k a plus minus minus 2I B T0 sine Ka times e to the power I Ka. This entire thing is minus sign actually, so we have a negative sign over here, and so this becomes positive over here. Okay, so let me write it, the entire thing here. Sorry, this e to the power Ika is not here because this was just a sine term. So we have this equation in the form E psi equals to EC plus 2 T0 psi minus T0 e to the power Ika psi plus 2I T0b sine Ka. Now first note that this term is actually a non-Hermitian term. Okay, when you write in matrix format, if you do the complex conjugate, in that case this e to the power this Ika, this becomes replaced by minus Ika, so this term is not the same anymore. Okay, so this part is not Hermitian, and so we are not getting a Hermitian matrix anymore. Okay, so we will discuss the essence of this, but first let us discuss a few other things. So as I stated that this term is H, this term is sigma, which is also known as the self energy, and this term is S, this is also known as the source term. Now note that our wave function phi n, this we took to be of the form of e to the power ikna plus c e to the power minus ikna, and we stressed on the fact that this part is the forward propagating wave that hits the channel, and so this term over here, this basically depends on this amplitude b of the forward propagating wave, so this must represent injection of electrons into the channel. Okay, so the source term over here, this basically represent injection of electrons into the channel. So and then what does this term represent? So this term is a non-Hermitian terms, and this basically represent extraction of electrons from the channel, or this term represents the fact that the channel wave function can actually leak into the contact. Okay, like the contact wave function can enter into the channel wave function can also leak into the contact. So this term basically represents the fact that the contact wave function can enter into the channel, and this term over here, this represents the fact that the channel wave function could actually leak into the contact, and that is why this term is basically proportional to the channel wave function psi, because it is a channel wave function which has the probability to leak into the contact. Okay, so this represents leakage of electrons into not electrons but electron wave function into the contact. Okay, the second question that might come into the mind was that earlier when we did not consider this coupling between channel and contact, and then contact wave function entering into the channel and channel wave function entering into the contact, then the wave function would have been simple, that this is basically E psi equal to H psi, where E is basically a number but H is basically a matrix. Okay, and H is used to be Hermitian. Now the obvious question that one may ask is that now this E psi is not equal to some Hermitian matrix times psi. Okay, so and this is the term that makes it non-Hermitian basically. So what has basically changed? So what has changed such that the matrix multiplying psi, this wave function psi, is not Hermitian anymore, and the answer is the fact that now the wave functions can leak from the channel. Earlier we considered a closed system, so earlier we considered a closed system where we have the Hamiltonian to be Hermitian. Now this system is basically open. Okay, we are only writing the equation for this wave function psi, and psi can basically leak into the contact. So this system is basically an open system now. Open system is where the channel wave function can leak into the contact, okay, into the surroundings. So we still have the Hamiltonian to be Hermitian, but we have a term which is non-Hermitian, which is known as the self energy. And I repeat again that this self energy basically represents leakage of electron wave function into the contact, and in generic term it is like incorporating boundary conditions, and here the boundary conditions are basically the effect of the contact on the channel wave function. Okay, the effect of the contact on the channel wave function. Okay. So I repeat again that this basically represents the leakage of wave functions into the contact, the channel wave function into the contact, and this basically incorporates the boundary condition, which in this case the boundary of the channel is the contact. So it basically incorporates the effect of the contact on the channel wave function. Okay, and this is the source term. So this is the forward propagating wave that comes from the contact and hits the channel. Okay. Now the second question which you may ask is that this Hamiltonian H and this self energy sigma, they both multiply this wave function psi over here. So what is basically the difference between them? So the thing is that this Hamiltonian H and this self energy sigma are kind of on equal footing, but this self energy basically incorporates the effect of the surroundings on the channel. It incorporates the effect of channel leakage, and the mathematical difference is that it is an energy dependent term because it has this wave vector k over here. So this is an energy dependent term which basically makes this entire equation a non-trivial equation, because now earlier we had to earlier the Hamiltonian used to be constant, a constant matrix. Okay. Now within this equation itself we have its term which depends on energy, so it basically makes the solution of this equation difficult, and this has to be solved in an iterative way. But the thing is that we don't need to solve it because we do not now need the eigen energies of the system. So here we have to change our viewpoint. Earlier, when we are studying a system, for example, when we are studying this 1D potential well, we actually asked ourselves that what are the eigen energies of this system. So in other words, what is the solution to this equation E psi equals to H psi. Okay, and we got these discrete energy levels over here which we called as E1, E2, etc., E3. But now since this system, so I am just giving an example that now since this system can accept electrons from outside environment and can also leak electrons to the outside environment, our question is now kind of different. So right now the question is that if I inject or if I try to inject an electron at any arbitrary energy, for example an energy E, which does not coincide with one of the eigenenergies of the system, or it might coincide one of the eigenenergy of the system, we do not know that yet. The question now is, if we try to inject an electron at an energy E into this well, what is the response of the system? Okay, so I am trying to inject an electron at an energy E, and if this energy does not coincide with one of the energies of the system, then what is the response of the system? Will the electron stay? Will the electron leak out? Or how long would it stay inside the system, and etc., etc. Okay, so E in this case, which we are studying right now, so E in this case is no longer an eigenenergy of the entire system, but E kind of represents an independent variable, and we are looking for the answer that if we inject an electron at an energy E into the system, then what is the response of the system? Okay, or in other words, will the electron stay? How long would the electron stay? What is the time of injection? All these things. Okay, so E is no longer an eigenenergy of the system because we are not looking for eigenenergy anymore. Okay, we are looking for the response of the system when we try to inject an electron into at the energy E. And this kind of systems which can accept electrons from outside or which can leak electrons to the outside environment, these kind of systems are known as open systems. Or if it's a quantum system, this kind of system are known as open quantum systems. Okay, so let us now go to the generic formulation. So we have a contact which is shown in blue and a channel, and these two are basically coupled to each other, and then we need to find the equation of the wave function for this channel. Basically, we are interested in the equation of the wave function for the channel. For the contact we are not interested, because the channel is basically what it restricts the property of any given device. Okay, now the Hamiltonian or the Schrodinger's equation for the isolated contact would basically look like E phi r equal to HR phi r. So I repeat again in case you don't remember, E is the number, it is the eigenenergy. Phi r is basically a m cross 1 matrix where there are m points in the contact, or at least for computational perspective we have taken m lattice point inside the contacts, and we have taken, let us say, n lattice points inside the channel. Okay, so this is one in m cross 1 matrix, this is an m cross m matrix, and this is again an m cross 1 matrix, and m in this case, as I stated, is typically large because the contact is basically large. Okay, so this is a Schrodinger's equation for the isolated contact when it is not coupled to the channel. Okay, so isolated contact, we can write this equation as E I R minus HR phi r equal to 0, where IR is basically an identity matrix of m cross m size. So IR, this is basically an m cross m identity matrix. Okay, in this case when the channel is basically coupled to the contact, the wave function of the contact can basically leak into the channel. Okay, the wave function from the contact can leak into the channel because the contact basically drives current inside the channel. So the wave function from the contact has to leak inside the channel. So that is why we have to add a leakage term over here. So we replace our equation when the contact wave function leaks into the channel. This equation gets replaced by EIR minus HR plus I eta phi r equals to 0. So here eta is a very small term which basically indicates leakage of electrons into the channel, and we will later show that if eta is basically very small, in that case if the contact has a continuous density of state, then the results does not depend on this eta, but eta is important to actually take into account the leakage of contact wave function into the channel. Okay, so we have added here and small anti-Hermitian or non-Hermitian term over here. So this represents basically leakage of contact wave functions into the channel. Okay. Sorry, this is not equal to 0, but this is equal to some source term which we call SR over here. Now this SR is basically the source term. It basically indicates re-injection of electrons into the contact, and this since this term basically represents leakage of the contact wave function into the channel, so whatever wave function leaks inside the channel, that has to be replenished by some wave function that comes from outside, because otherwise the number of electrons inside the contact would basically decrease. So to maintain the contact at a constant electrochemical potential or at a constant Fermi energy, or to maintain electron balance inside the contact, once electron from the contact leaks inside the channel, that electron has also to be replenished. So this is basically the source term that replenishes electrons into the contact. Okay, so in this entire equation we have not added what is the effect of the channel on the contact, how the channel is coupled to the contact. We have only said that the contact wave function leaks out of the contact. This term I eta takes into account this leakage, and that leakage is replenished by this source term which is known as SR. Okay. Now remember that this term phi r, this is the wave function of the isolated contact. Now if the channel is basically coupled to the contact, in that case not the entire wave function can basically enter into the channel because the channel capacity is limited. So what will happen is that a large part of the wave function, or at least a part of the wave function, would be reflected back into the or scattered back into the contact. So let us denote by it by this term x over here. So this is the wave function that is scattered back into the channel into the contact from the channel. Okay, so now let me just write the total wave function. So the total wave function is psi r plus x. This is the total wave function inside the contact. Okay. So when we write our total equation for this system, for the contact and the channel, so this equation becomes EIR minus HR, which is the Hamiltonian for the isolated contact, plus I eta. This is for the contact part, and the contact wave function is phi r plus x, and then this is coupled to the channel with this term tau. So we have added this term tau over here. Actually we could call it minus tau for a compact form of the expression which comes later, and we put a dagger over here. So if we put tau dagger, it's just a change again in how we write the terms. It doesn't make any difference. So we have this wave function, channel wave function psi, and then if this is minus tau dagger, which is the complex conjugate transpose of tau, so this term basically becomes tau minus tau over here. Okay, and then so this is how the channel is coupled to the contact, and this denotes how the contact is coupled to the channel. Okay, and then here we have the Hamiltonian part of the isolated channel, which is EI minus H. Okay, and this is equal to a source term SR over here, just as we discussed before, because the contact wave function needs to be replenished. Okay, and this term is 0 over here because this channel basically draws its wave functions from the contact. So no external source is needed to replenish electrons into the channel. The channel wave function is replenished by the contact already, and this is replenished through this term minus tau over here. Okay, so this first equation basically becomes equal to EIR minus HR plus I eta. So this is a matrix basically, so I should put matrix notation here. Psi r plus x minus tau dagger, this is also a matrix. Psi is equal to SR, SR is also a matrix. Okay, so this is basically the first equation over here. Now earlier we have also discussed this equation, EIR minus HR plus I eta phi r, this is equal to SR. So if we subtract this equation from this equation over here, what we do get is EIR minus HR plus I eta x, this is equal to tau dagger psi. So this is the reason we put the negative in front of the tau dagger in the Hamiltonian, so that when we change side, it basically loses its negative sign. Okay, so this scattered wave x, this is equal to EIR minus HR plus I eta inverse tau dagger psi. So this is known as the Green's function for the isolated contact. Okay, so this is known as the Green's function of the isolated contact. Okay, and just as I stated that this term I eta, this eta is nothing but this is a very small quantity. So this is basically 0 plus IR, where 0 plus is a quantity which is near 0, and IR is basically the identity matrix of m cross m dimension, m cross m size. Okay, now let us go to this second equation. So this second equation that we get by multiplying this second row with this column vector over here. So this is equal to ei minus h psi equal to tau psi r plus x. So ei minus h psi equals to tau. So this is also a matrix, so I should put it in third brackets, equal to tau phi r plus x, and x we have already got from the last equation. So this is basically tau phi r plus g r tau dagger psi, sorry, g r tau dagger psi. So this is basically equal to tau phi r plus tau g r tau dagger psi. Now if I take this term towards the left, I basically get ei. I is an identity matrix of n cross n size. So I don't remember if I have told it, but this is an identity matrix of n cross n size, minus h. H is the Hamiltonian for the isolated contact. So minus h minus tau g r tau dagger psi equals to tau phi r. So remember that phi r is not the entire channel, entire contact wave function, but phi r is basically the forward propagating wave function. Okay, so forward propagating wave function that hits the channel, and the wave function that is scattered by the channel into the contact. This is basically this wave function x over here. Okay. It might not be a forward propagating wave only, but I mean, let me reframe the statement. So this is basically the contact wave function. Okay, this does not depend on the channel. This is the contact wave function that was existing already inside an isolated contact actually. Okay, so this might not only be the forward propagating wave, but this is kind of let us say a wave function that was already existing inside the isolated contact, and this is the wave function that is scattered from the channel into the contact. Okay, so tau phi r. So we get an equation of the form ei minus h minus sigma psi equals to S. So for the channel, this is our source term S over here, and again these two are matrices, so it should be put in third brackets. This is also a matrix. So this is the this term is basically sigma. Okay, and this entire thing is the source term S. So what does S do? So S basically replenishes electrons from the contact into the channel, and this term sigma, this basically takes into account the boundary condition, and it takes into account the fact that the channel wave function basically leaks into the contact. So let us do up to here today. Thank you everyone.